Welcome to the first lesson of Chapter 9, Differentiation from Year 2 Pure Mathematics. And today we're going to do something very exciting. We're going to differentiate from first principles. And you've seen this in Year 1 differentiation, where we differentiate polynomials term by term. This time we're going to look at how to differentiate trigonometric functions. And we're also going to look at the exponential function and, not for the faint-hearted, the natural logarithm as well. Okay, now there's quite a few key pieces of information you're going to need beforehand, which are provided for you in the useful definitions. So we've got the compound angle formulae from trigonometry, which you met in chapter 7. There's the definition of the derivative from first principles, which is given to you in the formula booklet that was introduced last year. We've also got the small angle approximations here. Okay, now these were also introduced when we did trigonometry as an add-on to the work you did on radians. And finally, we have this definition you might not have seen before of the the exponential function. Now, it's not the exponential function per se. This is just the value e, the 2.71 irrational number, and it can be defined using this compound interest definition, where the n tends to infinity and we're adding on a smaller and smaller amount. So that's something you can try out maybe on a spreadsheet if you want to see how that works. Put in some values of n into that expression and then take the limit, and you'll see it approaching e. It's quite impressive. Okay, so that's the introduction. Now, please pause the video, look over the useful definitions, and see if you can answer the questions in the warm-up. Okay, and let's go through them one by one. So for question 1, I've just written out the definition from first principles again of a function f of x. Now, what we can do is we can define our f of x based on what's given to us in the question. So we're proving from first principles that the derivative of 3x squared is 6x. So the 3x squared is the function f of x. So let's start with that, and then we can continue and use the substitutions. So we're going to have f of x is equal to 3x squared. Okay, so that's just from the question. Now, part of our substitution that we're going to make into this expression on the right with the limit is we have to make the substitution for f of x plus h. Okay, we've got f of x, we've just written that down. So we need to figure out what f of x plus h would be. So let's do that. Now, let's just be very careful how we substitute this in. So instead of substituting x into my function, I'm substituting in x with h added, like that. Okay, so in other words, wherever I see an x in my function, as in I see an x here, and this is a function in terms of x, so wherever I see an x plus h now in my function, I have to replace x with x plus h. Okay, in the same way that in my function, x is consistent throughout, now x plus h has to be consistent throughout. So in case you didn't understand what I meant, it probably will become clear now. So I'm going to replace the x with x plus h now. So it's going to be not 3x squared, but 3 multiplied by x plus h all squared. Okay, I hope that's clear. So for example, if it wasn't x, if it was y, f of y would be 3y squared. Yeah, okay, and similarly, f of x plus h would be 3 lots of x plus h squared. Okay, so we've got that. Now we can substitute everything into the derivative. So let's see what happens now. So looking at the right-hand side, we know this is just going to be equal to the derivative. We've got the limit So we'll take the limit at the end. We're going to let h approach 0. So h is infinitesimally small. And we know what x plus h is with f done to it. We've just written it out. So we've got 3 multiplied by x plus h all squared. So that corresponds to the f of x plus h in the expression. Then I'm going to subtract f of x, which is, of course, 3x squared. And then the whole thing is going to be divided by h. And I just want to stress this substitution process again, because it's really important we get this right. So you can see I've highlighted the f of x plus h in green at the top here. So that corresponds to this expression here, which we've just established in some rough work above. And we've also got the f of x here, okay, which we wrote here and is now substituted in here. So it all corresponds. Now, all we have to do is expand, simplify, and see what happens. Now, don't forget, you're going to have to keep this limit notation at the front because we are going to be taking limits later. Okay, let's expand and simplify. So in the numerator, we're going to have 3 lots of, and if I just square everything in there, we're going to get x squared added to 2xh added to h squared. Okay, and then we're going to subtract 3x squared from all that, and that's all going to be over h. Okay, now we're going to multiply the bracket by 3. So this is going to be the limit as h approaches 0. And if I just do the top, multiply everything by 3, we're going to have 3x squared plus 6xh plus 3h squared. Okay, that's all multiplied by 3. Then we're going to subtract 3x squared. And the whole thing is divided by h. Now, if you've done this correctly, you'll know something happening straight away. The f of x part should cancel with a term in the f of x plus h part. Now, what I mean is the 3x squared here and the 3x squared here, because it's subtracted, will cancel out. So they're gone. Now, that should happen because if you know from differentiation, the power is reduced by 1. That's part of the process, isn't it? And that's why it's because the function terms are subtracted. Okay, so there's no longer an x squared term in this expression. The highest power of x we now have is 1 in the 6xh term. Right, okay, so we can also cancel out the h's as well. We've got 2 terms left over, and you can see that I'm going to have cancellation of h there. Okay, and I'm going to have cancellation of h here as well. Now, you can do that in an extra step if you want to, but I'm just conscious of space. So this is going to give me the limit as h approaches 0. And what do we have left? Well, we're going to have 6x because the h term has the h factor has cancelled, and then we're going to be adding 3h. Okay, and remember, I've not taken the limit yet, so it's the limit of as h approaches 0 of all that. So anything with h in becomes infinitesimally small. Okay, so you can ignore any term that contains h because it's a limit. That's the definition of what a limit is. So therefore, let's try that again. Therefore, as h approaches 0, 6x plus 3h approaches 6x. Okay, so there's our answer. Okay, so there's the derivative. It's 6x. Okay, so we can now state our answer. So therefore, f dash x in this instance is equal to 6x. Okay, and the great thing about this when you're doing it from first principles is they either give you the answer, which they have done, okay, or you can just use those laws where the power multiplies the coefficient at the front. So it's 3 multiplied by 2 here, and then the power drops by 1, which of course is 6x. Okay, so that concludes warm-up question 1. Okay, now for question 2, I've just written down the small angle approximations for sine and cosine. Okay, and we know we're going to use those because it says for small values in the question. And if you look at the expressions themselves, these are approximations, aren't they? So sine h over h is approximately the same as 1. So if I'm using this small angle approximation here, to put it in the context of this question, we just need to replace x with h. So in other words, in the context of this question, we have sine of h must be approximately equal to h for small h, okay? Only applies when h is small, but that's given to us in the question. So that means that in our expression, if we look at the left-hand side, this expression here, the sine h, can be replaced with h, can't it? So it's quite simple. So on the left-hand side, we're simply going to get h divided by itself, okay? Because the sine h is just going to be replaced with h. Okay, so that means that which is approximately 1 when h is small. Okay, it is 1 in fact, in reality, okay, because h divided by itself is 1, but because we are approximating sine h with h, we keep the approximation symbol there, simply because it's this term here in the numerator is an approximation. So it's no longer, it's not exactly h, it's probably going to be slightly different. Okay, so we keep the approximation symbol in there. And moving on to part B, we have the same idea. We're going to replace cos x, or sorry, cos h with the expression that we've got from the small angle approximation. So this expression here. And in the context of the question, we just need to replace the x with h. So I'm just going to do that first. So we have cos of h would be approximately the same as 1 subtract, now it'll be h squared divided by 2, okay? Okay, now that means that I take this expression on the right and I can substitute it for the cos h right here. So let's do that. So on the left-hand side again, just have a look at this. On the left-hand side, we're going to get the expression I've just suggested. So 1 subtract h squared over 2. Okay, that's replacing the cos h. So I'll just show the correspondence there. I'll shade it in pink. So I've just replaced cos h with that. Then I subtract 1 from that, and then I divide everything by h. Okay, now immediately you'll see that the 1 on both sides is a positive 1, plus 1 there, and the negative 1 will just cancel out. So we're left with negative h squared over 2 divided by h. Now, again, you can do this in another step if you want to, so I'll just do that. So it's negative h squared over 2 all over h. Now we can cancel out the h's. So we've got a h there and h squared there, so that's going to reduce to h. And I've just realized that should be roughly equal to, I apologize, which is approximately the same as negative h over 2, which I believe is what is given. So that's quite useful. So it's again, it's an approximation because we are replacing the exact value cos h with an approximation 1 subtract h squared over 2. So hence the approximation. Okay, now for question 3, I've just written out the definition of the small angle approximation for E, and I've also put it in the context of this question. So I've replaced the x part with h. And you can see in the question what we have to do, it's another show that, isn't it? So we have to show that this left-hand expression here does indeed simplify to 1 plus h over 2 if h is small. Okay, I'll stress that again, for small values of h only. Okay, it's approximately true. And this expression that I've written out, e to the x and e to the h as well, these correspond to small values of h when when you look at the exponential function. Okay, let's do this. So on the left-hand side, let's see what happens. Does it indeed simplify to what we want? Okay, so I'm going to replace the e to the h with this 3-term polynomial. So we're going to have 1 plus h squared over 2, which corresponds to that. Then I have to subtract 1. And then I have to divide the whole thing by h. Okay, so once again, we get this nice cancellation, don't we? We get a removal of the 2 constants, 1. Okay, so they're gone. 1 subtract 1 is, of course, 0. And the remaining expression is divided by h. So again, I'll do this in an extra step. So because I've replaced e to the h with this polynomial, this is now approximately true. Okay, so it's approximately going to be h plus h squared over 2 divided by h. In fact, just thinking about it, that's not strictly true, is it? It was the first step that is the approximation. Let's get this right. So the first step is the approximation of this, okay? Because that's where I've replaced e to the h with the polynomial. Yeah, not in the step I've just done. So that can be a straight equal sign. Okay, I hope that's clear, guys. I'm sorry about that. So let's just continue. So we've got cancellation here. Okay, and also cancellation here. So dividing everything by h. What do we have left? Well, we're going to have 1 with h over 2 added on. Okay, which corresponds to what we were given. Okay, and for the final question, number 4, another quite involved question. We have to find the equation of the normal to the curve. Now, remember that the normal is a straight line, okay, that is perpendicular to the gradient of the curve at that point. Okay, so the normal may change across the curve, if it is indeed a curve, as the gradient changes. So the normal is always perpendicular to the gradient. Okay, just something you need to be aware of. So let's go through the process. Now, to find the normal, there's a few steps we have to go through. I've written down the equation of the curve again, and we'll worry about how to write the answer later. And the point we're interested in is when x equals 1. Again, we'll look at that in a second. So we've got the equation of the curve. We need to find out what the gradient function of the curve is. Well, we've actually differentiated this from first principles already. So even if you didn't know how to do this, the answer was given in question 1, wasn't it? So if we differentiate that using the rule, 2 multiplied by 3, and then remove 1 from the power. So multiply those 2 together, and then take 1 off the power. So we're going to get 6x, as you already have seen. Okay, so the gradient at any point on that curve, so the measure of the slope or the incline, however you want to call it, at any point on that curve is itself a straight line function. So it's 6 multiplied by whatever the x value is at that point. So that's good. So we can now say, so therefore, when x equals 1, that's the point we're given here, okay? The gradient function will have a specific value. It will be 6 multiplied by 1, just sub it in, which of course is just 6. So when x is 1, the gradient is 6. Okay, so that's the gradient of the tangent. So I might just make a comment here. So therefore, so the gradient of the tangent to the curve when x equals 1 is 6. All right, just for a concept check there, I just wanted to make sure you remember what the gradient actually tells us. Now then, so that was the tangent. Okay, we're not interested in the tangent. We need the normal. So you should know how to find the normal. So we take the negative reciprocal. So let's make a note. So the negative reciprocal of 6, which is the value we found, gives us the gradient of the normal. So that makes it perpendicular to the tangent. Okay, you don't have to write all this down yourself, but if you struggled with this question or you needed to revise it a bit more, that's the process. Okay, so let's just write this down now. So therefore, the gradient of the perpendicular or the normal, you can use that symbol if you want to. Gradient of the normal is going to be the negative reciprocal of 6, which is of course -1 over 6. And if you're wondering what I've just written down, remember m represents the gradient on a straight line graph, mx plus c. This symbol here, it shows two perpendicular lines. So this represents perpendicular, which we can also shorten to perp. Okay. Right, so now we've got all that. We've got the gradient of our normal. What else do we need? Well, if you've got the gradient of the line, we need to fix the line in a particular place. And we know that x equals 1. So we also need a pair of coordinates, don't we? So let's find out what the y value is going to be when x equals 1. So when x equals 1, what does y equal? Well, you just substitute 1 into your curve, and it will tell you what the y value would be. So it's just going to be 3. Okay? From the curve, okay? So now we've got everything we need. We've got a pair of coordinates and we've got the gradient. So I'm just going to partition the board so we can now figure out the equation of the line. So I'm going to use the form of the equation of the line that you learned in year 1, which takes into account the two coordinates x and y at that point. So it's going to be y subtract y1 is equal to the gradient multiplied by x subtract x1. You don't have to do it like this. It's just whatever's more efficient given the circumstances. Now, just to make it really clear, what I mean by y1 and x1, so we'll call this x1 and we'll call the y value y1, okay? So they correspond. All right, so there's the y1 all there, and the x1 is there. Okay, so we're nearly finished. So we just sub everything in now. So we're going to have y subtract y1, which is obviously 3, is equal to the gradient, which is -1/6, multiplied by x subtract x1, which is 1. Now, that would be admissible if it just asks you to find the equation of the normal. That is an equation of a straight line, no doubt about it. But we have to, and if you read the questions really carefully, you'll see this, we have to write it in this form, and it's a little bit unclear on here, so a spell check didn't like it, does it? So ax plus by plus c equals 0, where a, b, and c are integers. So you can see at the moment, because we've got a 6 in the denominator here, we've got a fraction, we don't have any integers. So a good thing to do would be probably to expand and multiply everything by 6, and then hopefully we'll get everything in the form that it wants. So I'll just expand the bracket. So we've got y subtract 3 would equal -1/6x, and then don't forget we've got a double negative, so that's going to be plus 1/6. Great. Now we can multiply everything by 6 to remove the fraction. So let's do that. So we're going to have 6y subtract 18 is equal to -x, because the 6 will clear, plus 1. Right, we've got integers everywhere now. We just need to get everything onto one side of the equation. So I'm going to add x and subtract 1 from both sides of this equation. So if I add x, so this is my final step, I'm going to have x. Okay, I'm going to keep the 6y where it is. And then if I subtract 1, I should have 0 on the right-hand side. And there we have the equation of the normal, okay, where a, b, and c are integers. So again, just to top it off, we now can see that a would just be 1, b would be 6, and c would be -19. Okay, all integers, so it checks out. Okay, to get us started, we're going to look at further differentiation from first principles, and we're going to start specifically with sine x. Now, this is a rather interesting result here. If you differentiate sine x, we get the cosine of x. Okay, and we're going to prove this result from first principles now. So the first thing to do is to define what f of x is going to be. So in this case, obviously f of x is the thing we're trying to differentiate. So that's going to be sine x. All right. We can also write out the definition. So remember that the derivative of x, or sorry, the derivative of f of x is equal to the limit as h approaches 0 of the difference between f of x plus h, so that's when f of x plus h is substituted into f, and f of x itself, all over h. Okay, so that's the definition from first principles. Now then, the next step is to make that substitution of x plus h into our function. So I'll do that as a bit of rough work just here. So if I do that, we're going to replace the x that we can see substituted in this function, and I'm going to replace the bit I've highlighted in yellow with x plus h. All right. So if I do that, so I'll put that in red so it's really clear. So we've got x plus h in there, and on the right-hand side, we also replace the x with x plus h. Like that. Okay. So now we've got that, you'll notice something hopefully quite familiar on the right-hand side. We can see that we've got the sine of the sum of two possible angles here, if you like. So the sine of x plus h. Now, we've got we've got some tools we can use to break this open. So we can actually use the compound angle formula for sine of A plus B. So that I've provided for you in the useful definitions. And because you've done it a few times, I'll just go straight ahead and apply it. So in this instance, we're going to have applying the identity, sine of x multiplied by the cosine of h plus the cosine of x multiplied by the sine of h. Now, if you're not comfortable with that, just have a look at the useful definitions and remember you're going to replace, so if it's written like this, I'll just do a little aside up here. If you have the sine of A plus B, then obviously you would have A would be equal to X in this instance, and the B would be equal to H, okay? So that's all I've done, and I've just used the identity. Now we've got that, and we've broken open the bracket, we can substitute everything into our definition for a derivative. So I'm going to do that now. So we're going to have f dash x, and don't forget the limit as h approaches 0. That's really important. It wouldn't be a correct definition without it. And we'll substitute in everything we've discovered so far. So we're going to have the sine of x multiplied by the cosine of h added to the cosine of x multiplied by the sine of h. And remember, of course, I'm just going to highlight this. It's really important. All this stuff here corresponds to all this stuff, which in turn corresponds to all this stuff. It's all f of x plus h, isn't it? Okay, because f of x is, of course, sine x. Now, let's carry on. So we're going to subtract now f of x. So let's just confirm what f of x is. So f of x is this bit, and we defined it as sine x, didn't we, right here? So let's substitute f of x with sine x. Okay, and all that is going to be divided by h. Right, now we're, and I'll just show where I've made that substitution. So that's the f of x part all corresponding. So now we're looking at it and think, well, what can we do next? We can't collect any like terms. And the sine x on the right-hand side that's being subtracted won't cancel with a positive sine x like we've seen previously. So what can we do? Well, what we can actually do is we can do a bit of factorization. We've got a sine x term here, and we've also got a sine x term here, so that's good. So maybe we could factor out the sine x. Perhaps that would work. So let's do that. So our next step is to take the limit as h approaches 0. And I'm going to factor out the sine x in the numerator. So we'll put the sine x on the outside. Now, what do I have left over? Well, I'm going to have cos of h, okay, subtract 1. Okay, I think that makes sense. So I've taken the two terms that contain sine x, factored out the sine x, and that's what we've got left. We've also got a cos x multiplied by sine x left over. So I'm going to add that on. Like so. And all that is being divided by h. Now we're going to apply a property, or an axiom, if you like, of limits. Limits are just like derivatives, are linear. They're linear operators. So that means that you can split them up according to each term. So I can now split this single limit into two limits. So when I say this is a single limit, I could, in theory, put brackets around all this. Okay, but because there's an addition sign here, I can now split it into 2. Okay, so I'm going to do that now. So let's split this into 2. So this is the limit as h approaches 0. And I'm going to have sine of x multiplying cos h subtract 1 all over h. That's my first limit. Added to the limit as h approaches 0 of cos x cos h over h. Okay, now that's not sorcery. Okay, that's legitimate. That's a legitimate step. Limits are linear linear operators. Now then, you might notice something interesting. And I've just realized I've just made a type. I've just made a mistake. I apologize. That should be sine h. Sorry about that, guys. Okay, that's better. Now, you should notice something interesting now. So we're going to be taking the limits. Now, the limits only apply to any terms with containing h. Okay, so what I mean is this limit is going to be acting on any of the terms that contain h. Now, granted, we've got a sine x as a factor, but it's only going to be acting on this part of the expression. Okay, so you can, in theory, or in practice even, you can factor out the sine x so that it appears before the limit. Okay, which we can do in a second. And also in the second limit here, we're applying the limit as h approaches 0. It won't affect the cos x at all because there's no h in it, but it will affect the sine h over h. So what I can do is this. So I can say, all right, well, this is going to equal sine x multiplying, and I'm going to open a big bracket here, the limit as h approaches 0 of cos h subtract 1 over h. Okay, so that's fine. They're interchangeable. Remember, the sine x is not affected because there's no h in it. And we're adding. Now, in this instance, we can factor out the cos x. Okay, so it's going to be the cosine of x multiplied by, you probably guessed it already, the limit as h approaches 0 of what's left over. So that's going to be the sine of h over h. And just to be clear about what the limit does, we're reducing h to as close to 0 as possible. Okay, but in practice, you can't actually get there. It's just a direction. If you are pointed in that particular direction, where would you eventually end up if you could continue on going, i.e., if you could get to 0? That's what the limit does, because it's a useful tool, because in mathematics we can't be dividing by 0. Okay, h is not allowed to be 0 in this case because you'll be dividing by 0. It's not defined. But by making h as small as possible, we can anticipate the value that cos h subtract 1 over h or sine h over h might actually take if that could happen. Now, do we notice anything interesting? Well, if you go back to your warm-up from earlier, you'll notice that we've got the two results staring at us, haven't we? Okay, we've got the first limit of cos of h subtract 1 over h, which we looked at earlier, and we've also got the limit of sine h over h. Now then, if we look at these individually, we can actually replace them with specific values. Okay, now I'm running out of space, so you've got a bit more space on your page. I'm just going to continue the question up here on the right. Okay, so we don't lose sight of our working. Can you guys, when you're doing your notes, please continue down the page where you've got more space? So now what we have is we can apply our results from earlier. So we know that the cos of h subtract 1 over h, when h is small, So let's just make a note of this. Is approximately the same as minus h over 2, okay, when h is small. Okay, so what would happen now? So this is just an aside. What would happen if we now took the limit? So if we took the limit as h approaches 0 of this result, so let's do that. So the limit as h approaches 0 of what we've just talked about, cos of h subtract 1 over h. Well, that is almost the same, or it's equal to, I'll explain why it's equal to in a second, the limit as h approaches 0 of what we talked about earlier. So that would be negative h over 2. Now, the reason why we can put a straight equal sign there is because the limits are the same. We know that the cos h subtract 1 over h is not the same necessarily as negative h over 2. It depends on h being small. But in the limit, they are equal, okay, because we are letting h approach 0. So they share the same limit, okay? So that is true. Now, if we apply the limit, okay, so we let h approach 0, well, you can see straight away that the term on the right, because we've got a negative h in the numerator, is just going to become 0. So this limit is simply just going to turn into 0, okay? That is the limit. Okay, and you can verify this by plotting graphs and things on GeoGebra, but that's the case. So if we take the limit of all this, it shares the same limit as this, which of course equals 0. Okay, I hope that makes sense. Now then, we apply the same rationale to the second one. So the second one is, of course, the sine of h over h. So if we take the limit as h approaches 0 of sine of h over h, okay, I'll put that in brackets as well, why not? Now, we saw earlier that we get equality, of course, because they're sharing limits here. It's equal to the limit as h approaches 0 of, well, it was just h over h, wasn't it, which is just 1. Now, when this happens, so it's done for you, isn't it? There's no more h term to worry about, okay? So h approaching 0 has no effect on this whatsoever. So the answer is, of course, just going to be 1. And it's the same reason why in the previous steps we can quite easily just remove, or not remove, but factor out the cos x and the sin x and interchange them with the limit, because they are not affected by the limit. The limit is only applied to h, okay? So we have two results. So we have these two limits, and we now know, if we just go back to those previous steps, that this limit on the left, so I'm just going to do this quite crudely here, this is just going to approach 0, as we have just shown, and this limit here is going to approach 1. Now, what are the repercussions of that? Well, this means we're going to get our result. So therefore, we can now say that the derivative of x is just going to equal whatever's left. Now, if the first limit tends towards 0, this sine x term at the front, so all this is just going to die. It's gone, because that factor is approaching 0. So we're only left with cos x multiplied by the limit, which is 1. So we're going to be left with cos x. And if you want to just put it in, multiplied by 1, which is what it limits to. So the answer is just going to be cos x. Right, and that's the derivative. Now, what I recommend you do now, if you followed those steps and it made sense to you, I would recommend pausing the video and attempting to differentiate cosine of x using exactly the same process, the same thought process, the same technique, and see if you can show that the derivative of cos x is negative sine x. If you're not comfortable with that, just simply wait and I'll go through the question with you on the video. Okay, so we'll move on to the derivative of cos x now. Okay, so just to start us off with the cosine of x, I've just written out the definition once again. I've defined my function f of x as being cos x, which is what we're looking at this time. And I've also done the substitution of x plus h, which we substitute into the derivative definition. Now, we can break open this right-hand side again here using a compound angle identity. So this time we're going to use the cosine one. And this is one of the key differences between this question and the previous one. So if I use my compound angle identity, I'm going to get the cosine of x multiplied by the cosine of h, okay, making sure we use the correct one. Subtract the sine of x multiplied by the sine of h. Again, if you're not comfortable with this, go back to the formula booklet use the useful definitions at the start of the lesson. Try the substitution with a equals x and b equals h and just convince yourself that this is the case. So now let's substitute everything in to the definition. So let's do that. So the derivative, of course, is the limit. Really important part of the definition. Please do never drop it. Okay, even if you're being lazy, I strongly recommend you still write it in. So cos x, cos h. So this is the f of x plus h part. Subtract sine x, sine h. All right, and I'm just showing you what these correspond to. So this part here, oops. So that part that I've just written down is obviously the same as this, which is this part in the definition. Okay, so now we need to subtract f of x now. And we're just setting everything up, aren't we? So take off f of x, which is, of course, cos x. And you'll notice once again, we're not going to get the subtraction we wanted. As we got in earlier examples, we're going to have to maybe do some factorization. So let's do that. So therefore, let's factorize everything out. Okay, so which terms or which factors appear more than once? Well, let's have a look. Well, we've got it's the cos x, isn't it? So it's the cos x appears there and there. So we can factor out the cos x. So I'm going to do that now. So it's going to be cos x. And what is left over? Well, it's going to be cos h. Subtract 1. So this looks quite familiar, doesn't it? It looks like we've got the same factor as the previous example. And we've also got the sine x, sine h term as well. All of this is divided by h. Now we're at the stage where we can split our derivative into two limits. I always put the therefores. So the limit as h approaches 0, and we'll write two separate limits now, separated, of course, by the negative sign. Show you which the second negative sign. So this one. So I'll do it all in green. So we're going to have cos x multiplied by cos h subtract 1, all that divided by h. Okay, now we've got to be careful here. Notice it's a negative sign, so it's going to be the limit of all that. I'll just put in that blob there. So I'm going to be taking off the limit as h approaches 0 of whatever's left over. So that's going to be sine x sine h divided by h. Okay. And if you want to make this absolutely clear, we could stick all these in brackets as well. Okay, so we've got one limit subtracting another. Now, I explained, maybe over-explained in the previous example what happens next, but I'll just draw your attention to these factors again. So notice in the first limit, we've got the cos of h minus 1 divided by h all here, okay? And we're taking the limit as h approaches 0. Okay, similarly, in the second term, we've got the sine of h over h here, and the limit as h approaches 0. So I'm just going to move over to the left-hand side of the board now. And we'll continue the question over here. Again, please continue down your paper. You've got more space than I have, and I don't want to lose sight of the working. So we're going to rewrite it with the limits switched around, because we can factor out the cos x from the first limit and the sine x from the second limit, because they are not affected by the limit. There's no h term to speak of at all in those particular factors. So this is going to be f dash x is going to equal cos x. And then we put the bits I've highlighted together, multiplying the limit as h approaches 0 of cos h subtract 1 over h. And then I'm subtracting, don't forget it's a subtraction, the limit, I beg your pardon, sine x multiplying the limit as h approaches 0 of sine h over h, like that. And we can even put those in brackets as well. Okay. I mean, don't be put off by the limit. These are just going to be values. Okay. They're just numbers. Okay. So treat them like numbers, like coefficients. Now then, we've already evaluated these. I'm not going to argue the whole thing again. I'll just tell you that, of course, this approaches 0, that whole limit, and well, it doesn't approach 0. Sorry, we've got the limit built in. That's wrong. The limit equals 0. This whole limit equals 0. Okay, and the limit on the right is equal to 1. Okay, we've seen that already, so just get rid of that arrow. I would put the arrow in if I didn't have the limit written in there. Okay, just want to be as precise as possible so I don't confuse you. And I'll just rewrite that h there. Oops. Sorry, it's having pen trouble. Okay, now we can write down the answer. So this is interesting. So notice the first term is gone completely. So this is all just 0, it's gone. And what are we left with? Well, we are left with negative sine x multiplied by 1. Okay, so the answer is, of course, just going to be negative sine x. And there's our derivative. Really interesting results. Okay, so to put this into perspective or context, if you differentiate sine x, the gradient function is cos x, which is a 90-degree shift. So its own gradient function is a 90-degree shift of the function itself, which is quite extraordinary. And then we have similar behavior for cos x, except the derivative gives us negative sine x. It's just got a negative sign in front of it. Now, these differentiations from first principle, you will need to know how to do it. So it would be a good candidate for maybe a flashcard or something like that, and just practice them as an exercise every now and again when you're doing revision. So it is an exam requirement. However, in other types of questions where you're not asked to do it from first principles, you can just apply these results directly. So you're allowed to use the fact that the derivative of cos is negative sine and the derivative of sine is cos. Okay, it's only if you're asked to do it from first principles that you have to go through all these steps. Okay, so let's have a look at a couple more examples of this. Okay, now for the next one, we're going to differentiate e to the x from first principles. And the fantastic property of e is that it is its own derivative. And there's multiple ways of exploring this throughout the course, which can be quite exciting. But in this instance, we're going to look at the derivative from first principles now. And I've set up the definition once again. We've defined f of x. We've defined f of x plus h. So we're just going to substitute everything into the definition now. Okay, so therefore, we've got f dash x. So that's going to be the limit as h approaches 0. And we substitute everything in. So again, just to show you how these correspond. So this is f of x plus h. So I'm going to replace that first term there with that. And then f of x here, I can replace with just e to the x. Okay, as defined there. So let's do that. And there's no trig in this question, of course. None of that to worry about. So we have e to the power x plus h. Subtract e to the x. Okay, and that's all divided by h. So the question is now, what do we do with this? So, and we're taking the limit of all that, of course, as h approaches 0. Well, we can't see, well, there's no like terms to be collected, but again, look for a factorization. We can actually factorize this, and I'll just show you how, if you've not seen it already. This is the limit as h approaches 0 of, now if we just have a look at this first term here in the numerator. If you remember back from the work you did on indices back in year 1, right at the start, when we're adding the indices, of course, this is a product of two numbers with the same base. So I know that this expression here I can replace as e to the x multiplied by e to the h. Okay, because index laws say same base, the product becomes a sum in the power. Then I'm going to be subtracting e to the x and then all over h like that. And then obviously, well, you can put the brackets around that as well. Now we can see a factorization. So we can now see that we have an e to the x that we can now factorize out, sorry, from the numerator. So let's do that. That's going to be our next step. So this is going to be the limit as h approaches 0 of e to the x. Okay. And what do we have left over in the numerator? Well, we're going to have e to the h subtract 1. Oh, this is looking familiar as well, isn't it? Okay. All over h. Right. Now you'll remember from warm-up question 3, if you did it, we actually looked at rewriting e to the h subtract 1 over h using small angle approximations, the same as we did with sine and cosine. So let's just do the next step. We just need to interchange the limit and bring out anything that doesn't have h in it. Well, if we do that, this is going to be e to the x. I can swap the e to the x and the limit around because there's no h to worry about there. It's not going to be affected by the limit, so we can swap them over. And what do we have left? So it's going to be e to the h subtract 1 over h. Well, in the warm-up, of course, we saw that when h is small, the expression e to the h subtract 1 over h is the same or almost the same as 1 plus h over 2. That's what we saw in question 3. So I can now say, well, this is going to be exactly the same as e to the x multiplied by the limit as h approaches 0 of 1 plus h over 2. And again, I'll say it again just to reiterate and hopefully consolidate your learning. The two expressions are approximately the same. So the two expressions I'm talking about, this one and this one, are approximately the same when h is small. But look what we are doing. We are letting h approach 0. Well, approaching 0 doesn't get much smaller than that. So they share the limit. They are identical in the limit. So we can put a straight equals here and say that they are the same. Now we can apply the limit. And what do we get? Well, if we apply the limit, well, of course, what's going to happen when h is 0? Well, we're just going to get 1, aren't we? This term is just going to become 0. So we're just going to have e to the x multiplied by 1. So the whole thing is just equal to 1. And therefore we get e to the x. Okay, as our final answer. So the derivative of our function is e to the x. It's its own derivative. Okay, so that's the third one. Now, you'll notice on the right-hand side, we've got a little asterisk next to this. I'm not going to go through this derivative in this video, okay? I will do a separate video on the derivative for the natural log of x because it is a little bit more involved than what we've seen so far. And it is not a course requirement, but I think it's something really interesting that you might want to see. So you can move on to the next worked examples. And if you want to fill in the notes for the derivative of log of x, please go to the separate video which explains how to do it. Okay, so we're going to do some worked examples based on these new concepts now. For part A, we're just going to apply our new differentiation and combine it with what we learned in year 1. And while we get used to this, I just strongly recommend you follow the same procedure. Okay, don't try and do these too quickly because otherwise you'll make silly mistakes. So if you look at the question, we're going to differentiate it by finding dy by dx, and then we're going to find the second derivative. Now then, if I just write out the function we've been given, or the curve, we've got y equals 6. Now, I'm going to use brackets here just to make it absolutely clear that we've got these functions waiting to be differentiated. Okay, so I'm just going to put them in brackets. You don't have to do this, but I'm just drawing your attention to the sine x, the cosine x, etc. And you'll see why in a minute. It will hopefully help avoid making silly mistakes. So 6 sine x subtract 2 lots of cosine x. So we'll put that in as well. And then we have something a bit more familiar from last year, albeit a bit awkward looking. So I'm going to write this as a power using index laws. So this is going to be plus 4 x to the power 3 over 2. Now, if you're not convinced by that, I'll just do a little aside on this. So remember, of course, that we've got 4x cubed, well, x cubed square rooted. So this is in fact 4 multiplied by x cubed, but the x cubed part has a square root. So remember, that's raised to the power of half. Okay. And then index laws say that when you have a base to a particular power raised to another power, you multiply the powers together. So this is going to be 4x to the power 3 over 2. So yeah, one stuff, but I just wanted to go over it again just quickly. Now then, let's differentiate our curve the expression on the right hand side. So dy by dx, and we do this term by term. It's a linear operator. So the derivative of sine x, which we met very recently from first principles, is of course cosine x. And the fact that it's multiplied by 6 doesn't matter. Okay, so we're going to get 6 cosine x. Okay. Okay, as the derivative of sine x. And then we've got a subtraction, subtract 2 lots of the derivative of cosine x. Now you'll see why I've used the brackets here. In fact, I should have put brackets around this one. If I differentiate cosine x, what do I get? Well, I get negative sine x. So I'm going to put a negative sine x in there. Close that bracket. Okay, so that looks good. And then we differentiate the final term as normal, or as we did in year 1. So I multiply my coefficient by the power. So the power is, of course, 3 over 2 multiplied by the 4. Okay, and then the other thing I have to change is I have to subtract 1 from the power. Those are the rules. So 3 to the power 3 over 2, but with a 1 subtracted. All right. So let's put all this together now. So this is going to equal 6 cos x. And we have a double negative here. So we've got to be very careful. We've got a negative there and a negative there multiplied together. So that's going to be a positive. Hence, that's why I want you to avoid making silly errors. So that's going to be plus 2 sine x. And then if we just tidy this up, we're going to have 3 multiplied by 4, which is 12 divided by 2. So that's going to be plus 6 x to the power 1/2. Okay. Now, to finish it off, if you're asked to differentiate something and the curve, the expression for the curve has surds in it, or it's expressed in a particular way, it's good practice to make sure that your derivative is expressed in the same way. Okay, so I can replace the x to the half with root x. So I'm just going to do that now. So it's going to be 6 cos x plus 2 sine x plus 6, and then I'm going to replace the x to the half with the square root of x. So they're in the same language essentially as the way the question's been put. Now for part B, we have to find the second derivative. Okay, well, we know the first derivative. Just write it out, dy by dx. And we had 6 lots of, I'm going to use the brackets again, cosine of x. Okay. And then plus 2 lots of sine x. And I'm not using the final step. I'm going to use the penultimate step, this one, because it's written in a form which is suitable for differentiation, where we have x to the power 1/2. So that's going to be plus 6x to the power 1/2. Okay, and we differentiate term by term. So first term, so derivative of cosine x here, of course, that's going to be negative sine x. So again, we've got to be careful here. So this is going to equal 6 multiplied by, okay, so what was that? Negative sine x, which is the derivative of cosine x, which you've just discovered. Okay, and the derivative of sine x is, of course, cos x. So that's going to be plus 2 multiplied by derivative of that, which is cos x. All right. And then the final term, we have to differentiate this. So that's going to be plus 1/2 multiplying the 6. And then we take 1 off the power. So that's going to be x to the power 1/2. But we have to subtract 1. Okay. let's do the next step. So we can probably remove the brackets now. So this is going to be -6 sine x, okay, plus 2 cosine x. And we've got half of 6, which is 3. So that's going to be plus 3. And then we're going to have a half subtract 1, which is x to the power -1/2. Okay, now once again, I need to write this in the form which it's been presented in the question. So the last step is going to rewrite that. So it's going to be -6 sine x plus 2 cosine x plus 3, and it's a negative power, so it's going to be reciprocal over root x, like that. Now, you'll notice when you do the differentiation of sine and cosine, no matter how many times you differentiate, you are simply just switching between sine and cosine all the time, okay? So there's no simplification as you would get with a positive integer power, such as like x squared. Because if you differentiate x squared, it's not long before you get 0. So the first derivative is of course 2x. The second derivative is 2. And then the third derivative will be 0. And then 0 forever and ever after that. With the trigonometry and with obviously fractional powers just tend to become more and more complex. Trigonometry just switches between sine and cosine all the time. So that's probably quite a nice property of the trigonometric derivatives here. Okay, so worked example 2, we have a curve and we have to find stationary points. Okay, so more excellent revision here from year 1 as well, built in, which is really nice. So the first thing, I'm just going to write down the equation of the curve. So it's y equals x subtract 2 sine x. Okay, and our job is to differentiate this. Now, I think a good idea, in fact, I'll just, let me just write that again. It looks a bit scruffy anyway. So I'm going to write it in a similar way to we did in the previous example. So it's going to be x subtract 2, and then I'm going to put some brackets in. Again, just to draw our attention to the fact that it's sine x here. Okay, whether you choose to adopt this is up to you, but you can see you might get into trouble with signs with certain questions. Right, okay. Dy by dx. Okay, so obviously finding stationary points means we have to find the points on the curve where the gradient is, of course, 0. Okay, and you'll know there's different types of stationary points. We don't need to determine what kind of stationary point it is, whether it's a maximum, minimum inflection. We just have to find out where the gradient is 0, where the graph is effectively horizontal. Okay, so let's differentiate. We've got the first term, differentiate x, of course. We should know that. So that's going to be 1. And then we have subtract 2, and then the derivative of sine, which we've just met, or not just met, but we have met now, is of course cosine. So that's going to be 2 multiplied by the cosine of x, and that's it. So that's the derivative done. Now we just make a statement to the examiner to show that we understand what stationary points are. So we can say at stationary points, with an ARY, not ERY, not like pens and pencils. At stationary points, dy by dx is equal to 0. So we just set our expression that we've just found for dy by dx here, set that equal to 0 and solve. And notice we've got an interval from 0 to 2 pi. So you can see how there is this cross-pollination, isn't there, between different topic areas in maths. There aren't really different topic areas. There's just different tools for solving problems, really. Okay, so therefore, we have 1 subtract 2 cosine x must equal 0. So I'm going to add cosine x to both sides. So we're going to have 1 is going to equal 2 cosine x. And then if I make cosine x a subject, I have to divide by 2. So therefore, 1 over 2 is equal to cos x. Now that we've got that, we've solved the equation essentially, but we've not solved it for x. We have solved it for cos x. Cos x is now, we now know, is a half. So I now need to solve this equation here, okay, in the interval that's been provided up in the top right. So I'm going to do that now. And this is a nice simple one, isn't it? So we're just solving the equation cos of x equals 1/2 in the interval specified here. So it's a full circle, 0 to 2 pi radians. So at this point, we can find our principal angle. So you'll need a calculator now. So x is the inverse cosine of 1/2. All right, so let's get the calculator. Is it in radians? Yes, it is. Okay, hopefully we're comfortable with radians now. So we do shift, cosine, and put in 0.5 or 1/2, however you want to do it. And we get pi over 3. Okay, so it's a standard answer, isn't it? All right, so we can write that exactly, which is good. I don't know why it just didn't occur to me that it was pi over 3. Must have had a slip there. Okay. Pi over 3, yes. Yeah. Standard angle. Silly. Right, so we've got that. That's good. And we can now use the cast diagram. And again, if you want to change it into degrees, you can do. It's completely up to you. Makes it easier for you. Don't begrudge you that. That's absolutely fine. CAST. Pi over 3 is called 60. So we're just going to put that where cosine is, of course, positive. This is a positive value here. Okay, so where cosine is positive, we'll just stick it on there. So pi over 3 in both quadrants. Okay, and we read off our solutions. So we started off doing differentiation. We're now solving a trigonometric equation. Yeah, this is what can happen. So x is going to equal pi over 3. That's the first solution. Okay, and the second answer is, of course, 2 pi subtract pi over 3. Well, if you want to just do a bit of rough work there, if I want to do 2 pi subtract pi over 3, you just essentially just need to work out what is 2 subtract a third, essentially, isn't it? So it's just 5 pi over 3. Okay, and those are the solutions. So we've now found out what x values will give us the stationary points. Now, the question actually states, if we always go back to the question when you think you've finished, because you might not have answered the question. It says find the coordinates of the stationary points. Okay, so we now know that there's 2 x coordinates that satisfy the equation. So we now need to find the actual coordinates themselves. Now, to do that, we take our first x coordinate here and we have to stick it into the equation for the curve, and that will give us the full coordinates. Okay, if it just said find the x coordinates, then we'd be done, but because it says find the coordinates, we have to find those ordered pairs. Okay, so I'll just do that. Let's go back up here. So when x is equal to pi over 3, what do we get? Well, so we get y is going to equal x itself, so that would be pi over 3. Subtract the sine of pi over 3. So you'd have to find out what the sine of pi over 3 is. Okay, so we should know that. But if you want to do it on your calculator, I wouldn't begrudge you. Okay, so that's going to be root 3 over 2. Okay, and I'm going to leave it like that because I don't really want to write as a decimal. That is an exact answer, so that's good. So we've got the first pair of coordinates there. And also when x is 5 pi over 3, okay, what happens? Well, the y coordinate is going to be 5 pi over 3. I'm just going to be careful here. So what happens if we substitute in 5 pi over 3? Well, you'll notice if we're taking the sine, the sine is essentially going to give us the same value, isn't it? Okay, it's just a case of whether it's going to be positive or negative. But what we know from the cast diagram that 5 pi over 3 is, of course, this angle here. It's in the fourth quadrant, or depending on how you look at it, it's in the cosine quadrant where cosine is positive. So we know that sine is, of course, negative in that quadrant. So that means that rather than getting root 3 over 2, we're going to get the negative counterpart. We're going to get negative root 3 over 2. So that means I'm going to be adding, or let me just make it a bit more clear. We're going to be subtracting a negative root 3 over 2. And I hadn't anticipated that I'd need that much space there. Oops. Okay. And just to tidy that up, so therefore y is going to be 5 pi over 3 plus root 3 over 2. Okay, so just to write these as coordinates, the first coordinate is going to be at pi over 3 and pi over 3 subtract root 3 over 2. That's the first coordinate, and again I'm running out of space. The second coordinate is going to be 5 pi over 3 and then pi over 3 plus root 3 over 2. So I apologize if you didn't have as much space to do that, but those are the final answers. So I'm just going to again just draw your attention to those there. Okay, so that's the first pair and that's the second pair. So always read the question, make sure you answer it in full. Okay, and now we've got one more example to have a look at. All right, for the final worked example, we'll draw on some of the other information that we've learned today. We've learnt, or we've seen, that the derivative of the natural log of x is, of course, 1 over x. Now, if you've seen that from first principles, great. If not, it doesn't matter. Okay, but we're going to use that in this question. And we've also seen that the derivative of e, okay, so the derivative of e, which remarkably gives you exactly the same function back. Okay, so the derivative of e to the x is indeed itself. Now, the nice thing about these two results is it makes the differentiation process quite straightforward, doesn't it? Particularly when we've got an expression on the right-hand side of this curve, such as this. So it's the natural log of x subtract 3 e to the x. So I'm just going to write that down. And this time we're finding the normal to the curve when x equals 1. And we went through example in warm-up question 4, how to find the normal to a curve. So we're going to put all these bits ideas together. Okay, so the curve has this equation. So it's the natural log of x and subtract 3. And I'm going to use those brackets again. Well, maybe I won't use the red. Okay, we'll subtract 3 e to the x. And we are going to differentiate the natural log of x and the e to the x separately. So we'll do that now. So therefore, the derivative of the curve at any point, and just apply the results now. So the derivative of ln x is, of course, 1 over x. And the derivative of e to the x is just e to the x. So I'll just write it in, subtract 3 e to the x. Okay, and there's the derivative done. And why are we finding the derivative? Well, we need to evaluate the gradient when x equals 1, as stipulated in the question. Once we have that, we can determine the value of the gradient of the normal. Okay, so we go through those same steps that we went through in worked example 4. So when x equals 1, and this is all revision now, so this is really important. Although this is year 2, we've actually finished the year 2 content. Yeah, in this question, we've done the differentiation of ln and e. Now we're just finding the normal, okay, and making substitutions into equations. That's all we're doing. So when x equals 1, dy by dx, okay, is going to equal whatever I get when I substitute 1 into the expression above. So that's going to be 1 divided by 1. Okay, so that's fine. That's defined, isn't it? Okay, subtract 3 multiplied by e to the power 1. Okay, and if you'll notice from the exam, the way it's written at the end, we're going to leave all this in terms of e. We want exact answers here. So this is going to give me 1 subtract 3e. Now that's the gradient of the tangent. I won't write it all out again. So hence, the gradient of the normal, so m perp, gradient of the normal, just if you didn't see the warm-up questions, that represents perpendicular. Okay, so the gradient of the perpendicular, or the gradient of the normal, is just going to be the negative reciprocal of what we got just now. So this bit, the negative reciprocal of that. And don't forget that it's the negative reciprocal. Okay, I'll do this in red to make it really clear. So it's going to be negative 1 over 1 subtract 3e. Now, it doesn't look as nice, but nevertheless, we've got it. So that's an important piece of information we've just discovered. Okay, now what else do we need to find the equation of the normal? Well, we need a pair of coordinates, don't we? We know x equals 1, so we also now need to figure out what the y coordinate would be when x equals 1. So let's do that. So when x equals 1, what does y equal? Well, y is going to be the natural log of 1. We'll put that in. Just subbing into the original curve, subtract 3e to the power 1, okay, which is obviously just e. Now, natural log of 1 is, of course, 0. So therefore, y is just going to be negative 3e. And we've got another important piece of information here. So we now know what the y coordinate is when x equals 1. Okay, so now we're in business. So now we can find the equation of the normal. So again, I'm going to use the information or the format from year 1, which uses the coordinates and the gradient. So I'll call x1 is equal to 1, y1 is equal to negative 3e, and m, the gradient, is equal to negative 1 over 1 subtract 3e. All that stuff we've already found, and I'm going to substitute all that into this formula. So y minus y1 is equal to the gradient m multiplied by x subtract x1. Okay, I'm just calling it m now. It doesn't really matter what we call it, but we know it's the gradient of the normal. Okay, hope that's all right. So everything, all this stuff is now just going to get substituted into our equation, and we've got to write it in the form required. So let's do that. So we're going to have y subtract y1. Now, y1 is a negative number, so that's going to be negative 3e. Be very careful with your signs. M is a negative also as well, so that's going to be negative 1 over 1 subtract 3e. And in the bracket, we have x subtract x1, which is nice and simple. That's just going to be 1. Right, so now that would constitute the equation of the normal. We've got to show that all this can be written in the form given up at the top. So this is going to be a big test of algebra skills here. So what can we see that we need to do? Well, first of all, we need to have all the terms on one side of the equation so that we have a 0 on the right. We also need to clear the fraction from the bottom here at some point. Okay, I think the first thing to do is just to expand the brackets as we did in the warm-up question. So let's expand and simplify. So we're going to have y plus 3e is going to equal negative 1 over 1 subtract 3e. Okay, now we're multiplying through inside the bracket, so I'm going to change that 1 to a negative x. Okay, so all that's going to be multiplying x first of all, and then I have to take all this and multiply it by negative 1. So that's going to create a sign change. So that's going to give me plus 1 over 1 subtract 3e. Okay, I hope that's all right. Now let's clear the denominator. Now you can see here this looks promising because I've now got the 1 subtract 3e appearing here. So if I multiply everything by 1 subtract 3e, it should be all right every term, and then hopefully we can collect it all together. Okay, now if you look at the way it's expressed, it's written on the left hand side. On the left hand side as a product of two linear expressions. So I can do that. I can multiply all of this by the 1 subtract 3e rather than doing it term by term. So that way it will look like the answer is supposed to. If that sentence made sense. Okay, multiplying by 1 subtract 3e now. So 1 subtract 3e multiplied by y plus 3e is equal to, and it will just clear everything on the right hand side. So I'll have negative x plus 1. And now we can add x and subtract 1 from both sides. So therefore, we have 1 subtract 3e multiplied by y plus 3e, add x, subtract 1 equals 0. And yes, that checks out. Okay, so it looks quite complicated, but it's just a case of, well, it's just testing your algebra skills, really. Okay, so just to reiterate, the A-level stuff, as in the year 2 stuff, ended in that step. Okay, the rest is just revision on year 1 tangents and normals work. Okay, so that concludes the first lesson on differentiation.